Hey, what's up guys? I am Bysisa. So today's episode is going to be on conversion reactor. So this is a sample problem given, and it says the interest in the production of hydrogen from hydrocarbons has developed considerably. Proficient production of hydrogen is an enabling technology which is directly related to the fuel cell energy conversion device, and the conversion of fuels to hydrogen can be carried out by partial oxidation. So the partial oxidation method relies on the reaction of fuel. So example, I have two reactions here. The first reaction, methane reacts with oxygen to produce carbon oxide with hydrogen. Also the second reaction, methane reacts with oxygen to produce carbon dioxide with hydrogen gas. So the first reaction, methane reacts with oxygen to produce carbon monoxide with hydrogen gas. Also the second reaction, I have methane reacts with oxygen to produce carbon dioxide with hydrogen gas. So it says you have to assume the first reaction here, the conversion reaction is to be taken as 32%. The second reaction is conversion reaction also to be taken as 68%. So you are asked to develop a model that represents the partial oxidation of methane to produce hydrogen. So also at the end of the question, you are to obtain the composition of the percentage composition of each component in vapour phase and also in the liquid phase. So the other part of the question, where the data is located, I have initially I have two streams. The first stream is methane, the second stream is air. So the first stream, I have a temperature of 50 degrees Celsius and a pressure of 4 bar and a molar flow rate of 100 kg mole per hour with a component mole fraction of 100%. So I have air with a temperature of 50 degrees Celsius with also a pressure of 4 bar and a molar flow rate of 520 kg mole per hour. So in this time around, I have nitrogen gas and oxygen gas as with a percentage with a mole fraction of 0.78 for nitrogen gas and 0.22 for oxygen gas. So these are my components. So let's proceed to the hysys simulation environment. So we now go to new. So we add our component. I have methane, then oxygen gas, then I have carbon monoxide, I have carbon dioxide, let me add, also I have carbon monoxide, then I have nitrogen, so let's check back the component and see whether we are. I have oxygen, nitrogen, methane, hydrogen. So I have to insert hydrogen. So also don't forget, in the search bar here you could either type the name of the component or its chemical formula or its synonym. So we now go to fluid package. So in this time around, our fluid package is going to be Peng Robinson. So also don't forget, I have two reactions, so I have to add my reactions here. So I go to add, it's conversion reaction, so I add. I have two reaction also. So after you have added your reaction path, so you double click on the first reaction, you add your components. So don't forget from the question, first reaction, this is our first reaction. I have methane react with oxygen to give the products as CO plus 2 molecules of hydrogen. At the reactant, I have methane react with oxygen to produce CO, carbon monoxide with hydrogen gas. So methane, since this is reactant, it goes with -1. So let's check the equation. The molecule for oxygen is half, so that is minus 0.5. Then here I have 1 for CO. Also for hydrogen gas is how much? Let me check the coefficient. I have 2. Going to 2. So you balance. So for the conversion reaction, I have, for first reaction I have 32%, so I have to insert my 32%. That is then for the second reaction, also I have methane reacts with oxygen to produce CO2 gas with hydrogen gas. So I have a reactant -1. I also have -1. Also here I have -1. Then I have 2. The product always goes with positive, not negative. So the reactants, since they are consumed, so they carry negative sign. So for the second reaction, which I'm solving right now, this is the second reaction. Methane has 1, oxygen has 1, also carbon dioxide has 1, then the last one has 2 molecules of hydrogen, that is 2. That is why maybe you might wonder how I insert such those values. So after this, so in this time around, the conversion reaction for second reaction is 68%, so I have to insert 68%. Here I go, 68%. So after this, now I add Bengal-Vincent. You have to add the reaction to the equation of states which you are using with. So I now go to my simulation. I have 2 streams. First stream, I have the second stream. So the first stream is methane. The second stream is so we have to console back the equation. So the first stream, that is methane, I have 50 degrees Celsius, 4 bar of pressure, 100 kg of per hour of molar fluoride, and composition to be 100%. So for methane, I have 50 the unit must correspond, so this is Fahrenheit Celsius. I have pressure of 4 bar. This is psi, so it has to be 4 bar. I have here to be molar flow of 100 kg mole per hour. This is pound mole per hour, kg mole per hour. Then the composition is 1, that is 100% for only methane. Okay, so here I have let's consult the question again 50, 4 bar and 520. I have the temperature. I have 50 degrees Celsius. I have 4 bar of pressure. Make sure the unit correspond. I also have 520. If I am not mistaken, let me check. 520. in kg mole per hour. Also, the composition for nitrogen, I have nitrogen 0.78, then oxygen 0.22. Then oxygen 0.22. So we now proceed to add our conversion reactor. So we now check the columns. This is combustion reactor, this is equilibrium reactor. So ours for this lesson is tutorial is conversion reactor. So we drag it here. So my first stream is methane, the second stream is air. So this is my vapour out. Let's give it a name, vapour 1. This is liquid 1. So here at the bottom it shows a red color, that is tells you that something is omitted or you need to add something to make the equation balance or the equation of states fixed. So we have to, and it says it requires a reaction set, so that means we have to introduce our reaction. So first the equation sets. So for equation 1, that is reaction 1. Look at them, reaction 1, reaction 2. So we are considering reaction 1 now. So using reaction 1, the molecular weight is for methane is 16.043 up to the last, that is hydrogen 2.06. Let's check for the second reaction and see. So for the second reaction also maintain. So it's only at the products. For in the case of reaction 1, it's at the product I only have carbon monoxide and hydrogen. So for the second reaction I have in the product side I have carbon dioxide with hydrogen. So that is why here carbon monoxide, I mean dioxide, is 44. For the in the case of reaction 1 is since it's the CO only, I have 28. So let's check the composition. So this is the vapour. Let's go to the composition. So using considering vapour phase, methane is -0.0. That means there is no methane in the vapour. Wow. So oxygen oxygen is at the vapour phase. I have 0.413. Carbon dioxide 0.0924. Carbon monoxide 0.0435. Nitrogen gas 0.551. and hydrogen I have 0.2717. so let's check at the liquid and see. So at the liquid there's no methane also, but I have oxygen to be 0.413, carbon dioxide to be 0.0924, carbon monoxide to be 0.0435, and nitrogen to be 0.5511, and hydrogen to be 0.2717. so the composition for both either reaction 1, both in the vapour and liquid, for the component that is from methane to hydrogen is the same. So the only thing that is missing, that is the methane. It doesn't have any percentage composition. So let's try reaction 2 and see. Let's try reaction 2 and see. Using reaction 2, I have oxygen to be, methane to be 0.000, for oxygen to be 0.0413. It's really the same thing, actually the same thing, yeah. So let's check for the liquid and see any difference. Still the methane. So this is it, how to solve any question. So using reaction 1 and reaction 2, both reaction has the same composition, both in liquid phase and in vapour phase. So this is it, how to solve any question on reaction conversion reactor. Thank you for watching. Also don't forget to subscribe. See you in the next episode.